Hello everyone. Our team is here to present our work on the autonomous self-driving wheelchair project sponsored by Cyberworks Robotics. We pursued this project to answer one main question. How can we give the freedom of mobility back to the user when on a wheelchair? Conventional wheelchairs can be inconvenient or janky for indoor movement. They also leave the users dependent on others. It comes with a steep learning curve, adding to the responsibility of the users. Our aim is to address these very challenges with a two pronged approach. One is a self autonomous solution that merges advanced hardware sensors with intelligent software capable of perceiving surroundings, planning routes, and executing the navigation independently. Second, we've implemented a fleet management system allowing for remote control of the wheelchair, further enhancing the mobility and freedom for the user. To implement these two approaches, the Skyline team made up of Chengyu, Hui, Brian, and I were tasked with the testing and implementation of autonomous navigation solutions by identifying corner cases and incorporating the feedback to implement a robust real-time navigation system that is resilient to changes in the environment, including lighting, occlusion, and minor displacements in the environment's objects. We have the fleet team consisting of Yenyan and Porter, who implemented the fleet management system to monitor and control the robotic fleet in real time. We have four high level objectives for our solution. Firstly, it must be safe such that our navigation system must not cause harm to the user or other objects and beings in the environment, mitigating risks, anticipating and reacting to potential hazardous solutions. Secondly, we want navigation that is graceful and comfortable to combat issues like motion sickness. Our controls are finely tuned to avoid overspeeding, jerks, or any form of drift. Thirdly, it has to be affordable. The major problem with the adoption of such solutions is accessibility, and hence we must utilize hardware and compute resources that are cost effective. Lastly, there must be a contingency plan for unforeseen circumstances where users can quickly and easily halt the wheelchair's operation if needed. There is also the option for a fleet management system which not only enables control of multiple robots but also ensures real time communication and basic security measures to protect the user data. We believe these requirements would enable widespread adoption of autonomous self driving wheelchairs, satisfying all stakeholders.
I'm here to introduce some of the hardware implementation of our project. On the left side of the screen, you can see the design of our mounters, well encoders designed by our group member Cheng Yu. On the right side, it is an all-in-one design of our border holders. Since our entire system is functioning based on a ROS system and a control system, we require the use of well encoders to read the numbers of times the motor rotated and the direction of the rotations to calculate the distance and direction of the movements of the robots. In order for the wheel encoder to rotate as the wheel rotates, we decided to design and 3D print the mounts for the encoders to make them in touch with the wheels. The all-in-one holder holds the Arduino Mega board, controller board, and the NVIDIA Jetson Nano. The Jetson Nano will process the images and calculate the best sailing to follow using the sailing drift detector algorithms we developed. The Arduino Mega board and the controller board will pass movement commands such as speed and directions to the motor through ROS. Finally, there is a NUC PC at the back of the wheelchair. It will process the deep learning information and will calculate the places that are suitable for movements. Then, that is our overall hardware implementation.
Our original Skyline system used a machine learning-based scaling detector. However, this method was too slow for real-world application at only 5 FPS. Therefore, we decided to switch over to using a line binary descriptor method, which has a performance of 30 FPS. As for our SLAM implementation, we used RTAP-map because it allows us to use one RealSense camera along with IMU to perform SLAM, localization, and visual odometry. Along with our navigation stack, we're able to compute a path for a wheelchair to take given a goal state. We implement a conversion node which will convert the command velocity from the navigation stack into a velocity and direction value for our Arduino controller. On the left, you can see the map area of our lab, which we will use in our demo. Another important component of our system is the task manager facilitating the switch between SLAM and ceiling drift detector. For when SLAM fails and can't localize, we can switch over to ceiling drift detector to guide the robot through an area until SLAM is able to localize again. The method for switching is manually calling the raw service, or based on the position/odometry of the wheelchair.
The GIF detector is mainly designed to work under some scenarios that SLAM tends to fail, like large and empty rooms. These limitations primarily arise due to the limited detection range of depth sensors, while other odometry methods like IMUs and the wheel encoders often lack reliability. Therefore, we use RGB camera to check movement. Like shown on the right side, as you can see, the features can be kept checking after the viewpoint changed. We utilize the movement of checked features to estimate the lateral drift of the wheelchair. Now on this PowerPoint, you can see the real environment testing results. It proves that this method can provide a reliable result of ground drift. The wheelchair motor control system consists of two integral components. The first part is responsible for detecting the status of other systems and accepts commands from all command sources. Depending on the mode, the corresponding commands are then transmitted to the controller. The second component, the closed-loop controller, utilizes the wheel encoder's reading to precisely control the wheelchair's movements. Following the command accepted,
This is the demonstration of our anti-collision test. On the top right, we have the Arvis visualization of EC165. On the bottom, we have the depth camera feed. Right now, we are setting the navigation goal for the wheelchair across the room, and we see that it starts executing its path. Soon, it detects a point cloud of a human object. It's able to detect it, stop for it, and continue executing its path. So in this, we have demonstrated safe navigation, and as we can see on the top right, there is a red line projecting outwards. That is the local path that is being planned. So we see that it's able to come to a desired stop wherever we've set the navigation goal. This is the demo of the navigation test with the user on board. To reiterate, the top right frame depicts the 2D projection of the EC165 3D map. Right now we see a pink arrow that sets the navigation goal for our wheelchair. The green trajectory depicts the global path, and the faint off-white projection from the wheelchair is the local path plan. We have our cost map parameter settings where we have customized the inflation radius to enhance the safety margin around the obstacles while also ensuring that the path that has been planned is not inefficient or conservative. Hence, we meet our objective for smooth and cost-effective autonomous navigation. The seamless maneuver is through the autonomous control logic, and the cost effectiveness is by avoiding the use of the commonly used but expensive LiDAR.
I'm going to demonstrate our fleet management system, which is designed to provide real-time monitoring and control for our robot fleets. Before we dive into the demo, let's take a closer look at the three interconnected parts of our system. First, we have the Fleet UI, which serves as the primary visual interface for users to access all the functionalities of the system. It is designed with a user-centric approach, providing an intuitive interaction experience. Within the Fleet UI, we have some amazing features. Now, here's something cool. The Fleet UI is fully mobile responsive, meaning you can access a system from your desktop, computer, tablet, or smartphone. Now, let's take a moment to see the mobile responsiveness of our Fleet UI. As you can see, I have the Fleet Management System open on my computer here. As I resize the web browser, you can see that it automatically adapts to the smaller screen size. The layout and element adjust themselves to provide an optimized user experience on different devices, just like it would on a mobile phone or tablet. And when I restore it to its original size, the Fleet UI seamlessly adjusts back to the standard desktop layout. Alright, now that we have covered the key aspects of our Fleet UI, let's dive into one of its exciting features, automatic robot dispatch. This feature simplifies the task assignment and execution process, making it so much easier to control the robot. To assign a task to a robot, you have two convenient options. First, you can select a task from the pull-down menus, just like these, and the system will take care of the rest. Alternatively, you can drag and drop the pin on the map to the desired location. so that you can quickly and precisely specify where you want the robot to go. But wait, there's more. We also offer manual robot control. You can set the velocity of the robot and using a control panel with buttons. These give you fine-grained control over the robot's movements, allowing you to navigate with ease.
The Fleet Server acts as a central server, facilitating communication between the Fleet UI and Fleet Client. Implemented using ROS2 Foxy, it collects data from individual robots and provides it to the Fleet UI. A core component of the Fleet Server is the robot registration process. This process allows the server to maintain up-to-date information with each robot state. Clients, as in the robots, publish their state updates to a specific ROS topic using a ROS publisher. The server's Robot Listener node subscribes to the topic, extracts the robot state information, and saves it for real-time fleet status updates. Another component of the Fleet Server is streaming video to Fleet UI. This uses the ROS Web Video Server package for streaming video. This package takes images published on ROS image topics and strings them together to publish as video. It supports 4 video streams simultaneously, allowing for video streams from the front, rear, left, and right angles of the wheelchair. The Fleet Client represents the onboard package implemented in ROS1 Melodic on each robot. It provides the necessary software stack and functionalities to enable seamless integration with the Fleet Server. The Fleet Client ensures that individual robots can communicate with the central server, transmit essential data, and execute commands received from the Fleet UI.